Welcome to the tutorial double-clad fibers for high-power fiber lasers. My name is Peterka. I come from the Institute of Photonics and Electronics of the Czech Academy of Sciences. And I was looking forward to meet you here in historic city of Prague and also in our laboratories of optical fiber technologies and fiber lasers. Because the lab tour was originally scheduled as a special event for the Europhoton conference. However, due to the pandemic, it could not happen. So I hope you will find occasion to see Prague and visit our laboratories sometimes in the future. This is the agenda of the tutorial. We will start with a brief introduction about fiber lasers, and then we will discuss thoroughly fundamental principles of double-clad fibers and pump absorption in the double-clad fibers. This part is often treated in literature somewhat shortly as something well-known and easy. On the other hand, we can see many mistakes and misunderstandings of this topic. So in this tutorial, it will be the opposite. The pump absorption will be the largest part of the tutorial, and only in the second half we will discuss somewhat shortly the limitation of double-clad fibers, large mode era fibers, pump combiners, technology of fabrication, characterization of the fibers, and emerging technologies and prospects. Now I will switch off the camera so that you will see the whole screen. When two are united and they become one, something new with new quality may be created. This is indeed valid also for the story of fiber lasers. However, the idea of fiber lasers is rather old. They were proposed probably before Theodor Neumann made shining his Rabi laser, and before the first single-mode optical fiber was drawn. It was drawn by the group of Erich Spitz and Jean-Claude Simon near Paris. These stories are fancy described in books by Jeff Hecht, The City of Light, and Beam, The Race to Make the Laser. Here you can see that Elias Schnitzer submitted his proposal even before the paper of Theodor Neumann was published. Eli Schnitzer put his proposal into reality very soon. His laser was made from neodymium glass fiber formed under heat into this spiral, and linear flash lamp was put inside the spiral. Look at the Neumann's laser. It was the opposite. Flash lamp was a spiral, and the Rabi rod was put inside the spiral. Simply speaking, whatever was the reason, fiber geometry matters. This might be a motto or secondary title of the whole lecture. The underlying motive of the story of double-clad fibers, that the geometry is so much important. Fiber lasers did not attract much attention in 60s and 70s, mainly due to lack of suitable optical pump source. It changed dramatically in 80s. Erbium fiber provides naturally just an ideal gain for telecom optical fibers in their low-loss spectral window around 50 nanometers. It was the component EDFA that made the broadband internet truly global. It was invented independently in the University of Southampton in Europe and in Bell Labs in the USA. Here you can see the amplifying medium, the erbium fiber, that shines green. The output power was limited by available pump source, a single transverse mode laser diode, to about hundreds of milliwatts. When we speak about higher power, we come to the topic of this lecture, the double-clad active fibers. It was again Elias Schnitzer who demonstrated it first time. It was in 1988. Nevertheless, the idea is older. It was patented by Robert Maurer in 1974. Have you heard this name? Yes, his team made the first low-loss optical fiber in Corning Glass Factory already 50 years ago in 1970. In parallel to Elias Schnitzer, Valentin Gapontsev investigated cladding pumping and developed his splendid all-fiber arrangement for pumping. We come back to it later. This tutorial was originally planned also as a teaser for a lab tour in Optical Fiber Technology laboratory here in Prague in the premises of the Czech Academy of Sciences. The lab tour was intended to be a special event of the Eurofoton conference. Unfortunately, the pandemic has changed many plans. So we will see at least some pictures and video from our lab in this lecture, and you can visit, at least virtually, some places in around our fiber drawing towers and around apparatus for making fiber preforms, like you see in this picture. And we hope we could see you in our labs during some future occasions. So we come to the main part of this lecture that is devoted to fundamental principles of double-clad fibers and pump absorption. What is double-clad fiber? Such optical fiber consists of a narrow core, typically supporting a single mode or few mode operation, and the core is doped with rare earth elements, for example erbium, ytterbium or thulium. The core is surrounded by inner cladding, usually pure silica, and the inner cladding is surrounded by medium with a lower refractive index. Here it is the polymer and here it is the air. And since the refractive index of the outer cladding is lower than that of silica, the inner cladding works as a waveguide for the pump, so it may be called pump core. The great advantage of this fiber is that the inner cladding has a large cross-section and large numerical aperture, so you can couple efficiently high power through low beam quality and high power laser diodes, multi-mode laser diodes, in the orders of watts or even kilowatts, using various clever ways of pump power combination. In the contrary, single-mode laser diodes can provide only hundreds of milliwatts into the narrow fiber core. Let's go back to the pump in the inner cladding. As it travels down the fiber, it may cross the inner core, the small core, it gets absorbed, and the excited ions emits in single transverse mode defined by the waveguide structure of the narrow core. So double-clad fiber works as efficient transformer of low quality, high power beam into the excellent beam quality with high power. Of course, at different wavelengths, because the pump wavelength is different from the emitted laser signal. This picture is also a very basic scheme of fiber laser in fabric parallel configuration that you can build easily in the laboratory. The perpendicularly cleaved fiber ends work as 4% mirrors. There is one simplification. The PEMP laser diode is usually not coupled directly to the active fiber. Firstly, it is coupled into passive fiber that forms the pigtail of the laser diode. The fiber has a lens fiber end for better coupling efficiency. So in laboratory, you would probably focus the pump with a lens like it is shown in this picture. In double-clad fibers, we have two families of rays of the pump. One group is the so-called skew rays. They propagate around the core and never cross it, so they cannot transfer the energy of the pump to the core. The other group is meridional rays. They cross the core and transfer the energy from the pump to the laser signal. In fact, circular fiber cross-section is the worst case for the pump absorption. See the red curve here. At the beginning, meridional rays have good overlap with the signal core and transfer the energy to the signal. However, as they get absorbed, we have only skew rays that do not mix with the meridional rays, and so we got saturation of pump absorption. To eliminate skew rays, fibers with irregular shape of fiber cladding were developed. In the first optimization step, we look for such a cross-section that provide proportional absorption with fiber lengths. So, in ideal case, pump absorption is given by the ratio of core area and cladding area, and it is proportional to the absorption cross-section in the core of the core. However, this is valid only for ideal absorption, and in most cases it is far from reality. Nevertheless, some people tend to use this formula to build their fiber laser. This is one of typical misunderstanding of principles of cladding pumping. So in the first optimization step, we look for optimal cross-section that provides homogeneous, it means constant absorption along the double-clad fiber. In fact, it would be nice to have different absorption at different places along the fiber. For example, at the beginning of the fiber where the pump is launched, we would like to have low absorption in order to minimize the heat load of the fiber at this place. So more sophisticated further optimization involves tailoring of absorption along the double-clad fiber. Let's look on the optimization problem from the ray optics perspective. We can learn from the mathematical theory of two-dimensional chaotic billiards. We can minimize saturation of pump absorption by cross-sections that provide so-called chaotic ray propagation. So if we describe the ray trajectory, or better say its projection to the fiber cross-section, so if we characterize it by point of reflection S at the circumference and angle of reflection alpha, so we got a phase diagram where here we have position of reflection and here we have angle of reflection. And for chaotic ray propagation, we will fill the phase diagram completely after sufficient reflections of the ray, without building acoustics. Natural circular shape of the fiber is the worst case of the fiber cross-section, so you see that we get only a single line in the phase diagram. It's not filled at all. D-shaped fiber is an example of ray propagation that provides good absorption. You can see that the phase diagram will be filled completely after sufficient reflections. D-shaped fiber, like this, is very easy to fabricate. It was proposed by Wentzel-Kramers, and such cross-section was widely used in 19th and early millennium. The ray tracing approach is described, for example, in the pioneering work done by Valérie Doya. However, not all D-shaped fibers provide good absorption. If the fiber thickness D is less than the circled radius R, then we see plenty of empty space in the phase diagram. So you can see that the rays builds acoustics. Many different cross-sectional shapes have been investigated. One that theoretically performed really good was the spiral shape with offset core. In this graph from the work of Kuznetsov and Moloney, you can see the pump absorption efficiency along the fiber. Pump absorption efficiency is simply the ratio of absorbed pump and the total input pump power. And this is the ideal absorption, and the absorption of the spiral cladding with offset core performs almost as good as ideal absorption. Here you can see the absorption of flower shape with central core. This is for the spiral cladding with central core, and here you can see very poor performance of circle fiber with central core. However, most theoretical optimization of pump absorption was long time restricted to approximation of straight fibers with no bending. And this is another deficiency of papers about theory of double-clad fibers, and it may lead to misunderstandings and misleading interpretations of theoretical results. Because unless you have stiff fiber waveguide like so-called rod fibers, it is very difficult to have fibers straight. Fibers are always somehow bent and twisted. Bending and twisting was used in experimental optimization of pump absorption by mode-scrambling. Typically, mode-scrambling was achieved by figure-8 spooling with or without twist. So here this is picture about twisted figure-8 layout. Very ingenious method is changing the convex and concave spooling in the so-called kidney-shaped spooling. Indeed, such smart coiling method may lead to significant improvement of pump absorption and overall performance of the fiber laser. What is interesting, it works well even for the case of double-clad fibers with circular cross-sections. Holger-Zellmer presented both experimental studies and theoretical modeling. They used so-called WKB method that was developed originally for modeling telecom multimode graded index fibers. But here it helps as well. It is a combination of ray tracing optics, from this we get trajectory of the ray, and wave optics. From this we get phase and transverse distribution of the modal field. And they search for mode mixing geometries that would increase pump absorption also in circular double-clad fibers. So using such a kidney-shaped geometry, they got up to 60% pump absorption efficiency, while for standard spool they might expect only about 10% absorption in circular fibers. You can see some periodic feature on the pump absorption. That is because changing of convex and concave cases of the spool. Theoretical modeling was verified with neodymium doped double-clad fiber made in IPHT in Jena. Kidney-shaped coil of circular fiber absorbed as efficiently as D-shaped fiber, but the length of the circular fiber has to be longer than the length of the D-shaped fiber. Here you can see results for different cladding shapes, including decentered fiber that was used by Alice Snitzer in his pioneering experiment from 1988. This is tomography of the preform of this fiber. Here is the offset core, and these waves or waved lines are artifacts of the computer tomography. These are not real features of the profile. The outer cladding was made with fluorinated silica layers. Indeed, offset core helps to increase the absorption efficiency. This is the triangular curve here. But anyway, only portion of skew rays can be absorbed. Better pump absorption is obtained in fibers with broken circular symmetry of their cross-sections, like the rectangular or D-shaped fibers where pump light propagates chaotically. Every launch ray of the pump will pass through the doped core at some position along the fiber. From now, we would like to show you pump absorption calculated using rigorous modeling by beam propagation method BPM, either based on finite element method or by FFT methods. Fiber bending is taken into account by modified refractive index approach. Later we extended this model in order to include also the twisting of the fiber. Because when you have fiber that is coiled on the spool and simultaneously twisted, the structure of the fiber rotates with respect to the spool. As the structure rotates with respect to the spool, then the modified refractive index also rotates with respect to the fiber. So we are rotating the modified refractive index also with respect to the fiber. So rotation of the modified refractive index profile around the structure mimics the twisting of the fiber. So we have investigated pump absorption in circular, stadium and hexagonal fibers, and in the so-called GTWave fiber bundle. It contains actually two fibers, one with a doped core and the other fiber was coreless for the pump beam. We assume a speckle beam that mimics a pump beam from a laser diode pigtail with 105 micrometer thick core. It is illustrated by these yellow circles. This is the speckle pattern of the pump pigtail. And we investigated effects of coiling, twisting, and pump injection orientation. It is the pump injection orientation is schematically shown here. So when it is oriented under 0 degree with respect to the spool, it means that it is coupled to the outer part of the fiber. This is 45 degree, 90 degree, 135 degree and 180 degree orientation with respect to the spool. It means that the pump is injected to the part that is close to the spool. For circular fiber, we got high saturation of the pump absorption, and the overall absorption was low, deeply below that what we expect from ideal absorption given by the ratio of the core to cladding area. Absorption does not depend very much on the pump launch conditions. The second graph shows the pump power fraction in the core of the circular fiber. It means that what is the pump overlap with the doped core, often designated as gamma. At the beginning, the overlap might be even higher than the ideal case given by ratio of the core to cladding area, but soon the overlap decreases by 15 dB in the 3-meter long fiber. Now see how different pump absorption we get in stadium-like fiber. It depends a lot on the pump launch condition, the orientation of the pump beam. The best absorption, very close to the ideal limit, we got for the twisted fiber. Here you can see the pump overlap with the core. The thick red line stands for the twisted case, and it has an oscillatory character below the ideal pump overlap. You may think that such theoretical guidelines may help to improve your experiment. But in this case it was a bit the other way around. First we draw a stadium-like fiber that was really ugly rocking when it was drawn. It means fiber orientation with respect to the spool changed several times per meter, like here in the twisted case. My colleagues from Fiber Technology Lab did not like it at all. But I tried the fiber in a laser experiment and it worked surprisingly well. My colleagues worked hard to improve the instability, so it means they draw the fiber without rocking. However, with the new fiber, I got very poor laser performance. So it means that the twist or rocking of the fiber helps to absorb the pump in double-clad fiber. We developed the theoretical model only after, so that we can explain the beneficial behavior of the twist. Another example where fiber twist help is the so-called GTV fiber bundle. Our model explains well why GTV fiber structure has such efficient pump absorption. You see here the cross section. This is not a single fiber, but it is actually a bundle, at least of 2 fibers, and the pump fiber only touches the fiber with the active core, like you see here. First, look at the 2 fibers without absorption. For straight fibers, about 40% of light is coupled from the pump fiber to the signal fiber, but the distribution is not changing a lot along the fiber. In the contrary, we can see periodic exchange of power between the 2 fibers along the fiber. It has important consequences for the 2 fiber bundle with absorption. While we got only negligible absorption for the untwisted case, here you can see in the green curve, there is almost no absorption. So for the pump, for the twisted case, you see exponentially decay with some oscillatory behavior in the signal core. So only the twist enables efficient pump absorption in the GTV fiber. Here you can see movie about pump absorption in a hexagonal fiber for the straight, bent, and simultaneously coiled and twisted geometry. The fiber is always illuminated by a speckle pattern that mimics the electromagnetic field in the pump pigtail with 105 micrometer diameter core. First millimeter of propagation is shown somewhat slowed down, and after 1 mm the movie runs faster. In all cases, pump becomes spread over the whole area of the cross-section, but in the case of bent fiber and bent and twisted fiber, the pump field is somewhat squeezed. Here in the bent only fiber, it's squeezed in the outer edge with respect to the spool. The straight and bent only fibers have a bluer center as the pump is depleted, thereby absorption. However, in the bent and twisted fiber, the rotated corners of the hexagon effectively mix the pump, and there is not a blue center in the middle. Lower pictures show longitudinal section at the fiber going through the fiber axis. So it goes through here. The cut goes through here. You can see here. So the spool is at the top of the figures here, here, and here. In the straight fiber, pump is spread over the whole cross section. And you can see the blue line in the middle. In the case of the bent fiber, the pump is squeezed to the outer edge of the fiber, and in the case of coiled and twisted fiber, again the pump is squeezed to the edge of the fiber, but it traverses through the core as it goes down the fiber. So what is the best fiber cross-section, and what is the best geometry of fiber layout? We can make some conclusions from these absorption graphs. First, note that we use normalized coordinate in order to compare different fiber shapes and different concentrations. For the straight case, the stadium fiber works somehow, and the two fiber bundle failed. Its absorption is very low. However, the overall absorption is not good in any case. For the bent case, we see that the stadium fiber is again the winner. And what really makes a difference is the fiber layout with simultaneous coiling and twisting. Hexagonal fiber, you see here the violet curve, has even better absorption than the ideal case for up to about 9 dB. For the level of absorption to about 9 dB, it is above the dashed line. Circular fiber is not good as it was expected, but look at the blue line, the GTV fiber bundle. Now it has constant absorption that we desire so much. You can see some tiny periodic features that correspond to the twisted rate. So with sufficiently long GTV fiber, you can absorb almost all the pump. Let's have a look on the fiber layout from the perspective of the overlap factor gamma. So we will study pump power fraction in the core. So here it is in the dB, decibels, along the fiber. For the ideal case, the overlap factor gamma is given simply by the ratio of the core area and the cladding area. For the straight fiber, the overlap is higher at the very beginning. It is higher than the ideal case, but it gets worse, gets down very quickly down the fiber. It's slightly better for the coiled case. You see here the blue line, but again it gets worse and worse as the pump propagates down the fiber. And look at for the coiled and twisted case. Here you can see that at the first half of the fiber, the average of the green curve is even above the optimal overlap for the straight fiber. We have experimentally verified enhancement of absorption in twisted hexagonal fiber doped with thulium. Here you can see the preform with hexagonal shaped, and this is the drawn fiber with thulium doped core. We measured the pump absorption in coiled fiber. This is the black line here. And the pump absorption in simultaneously coiled and twisted fiber. And we got quite significant difference at the pump wavelengths of 793 nanometers of about 8 dB for the 3 meter long hexagonal fiber. This test was done with halogen lamp, broadband halogen lamp, but we have tested it also by using pump laser diode at 790 nanometers, and we got similar results of pump difference between the coiled and twisted fiber. Then we tested it also in laser. So what about the laser performance? So does it help also in this case for fiber lasers? It is really hard to test. Imagine that you have 125 micrometer fiber, so it is always somewhat chaotically bent and twisted when you work with such a fiber in the lab. Only when it is pulled carefully in factory conditions, you can expect some proper regular geometry of the fiber layout. So we made the following two things. First, we cut fiber that is much shorter than the optimum length, so that the pump absorption enhancement would be pronounced. If the fiber is too long, so that everything is absorbed, all pump is absorbed anyway. And secondly, we hanged fiber to the ceiling first day, and we have introduced a tension by attaching a little weight to the other end. So by this, we hopefully to eliminate some memory of the polymer coating, and the fiber becomes straight again. The next day, we put down the fiber from the ceiling and we did the laser tests. So one mirror was attached to the pump end. It was a fiber brake grating, highly reflective and 1951 nanometers. And this is the multimode fiber as a pigtail from the laser diode. The other mirror was a perpendicularly cleaved fiber end with about 3.5% reflection. First, we measured the straight fiber laser output, then we coiled it carefully without introducing any twist, and then we coiled it and twisted it. We got this laser curve. And in fact, we got 50% increase of slope efficiency when we compare the slope efficiency of the straight fiber and the coiled and twisted fiber. It's not very practical to twist fiber that is already drawn. So to twist coiled fiber, it's not very practical. Better way is to twist the fiber during the drawing. So if the preform is rotated during drawing, the twist becomes frozen in the final product. Look here in the absorption curve. This narrow red curve with red dots is absorption of coiled fiber with no twist, and we got about 10 dB absorption of about 1.5 meter long fiber. Look here for the absorption of the same fiber, but that is twisted during drawing. We got at least 6 dB improvement in the peak absorption. So, in conclusion, the preform spinning improves pump absorption in double-clad fibers with the octagonal cross-section, even for the case of straight fibers, or in coiled fibers with large radius of the coil. So far, we have seen coiling in kidney-shaped and figure-8 spools, and more thoroughly we discussed twisting of the double-clad fibers, like hexagon and GTV fiber bundle on a standard cylindrical coil. One more special coiling we see here. It is the spiral coil, either pumped from the inner part of the spiral or here you can see the dashed line spiral that is pumped from the outer part of the spiral. Look here for the absorption graph, and you see that the octagonal and hexagonal fiber got almost the same overall absorption, but there is different absorption rate along the fiber. So when you pump it from the outer part of the spiral, you got smaller or slower absorption rate at the beginning of the fiber and higher absorption rate at the end. And this is rather advantageous, because at the pump side of the fiber you should have lower absorption. It means you have lower heat load. And on the opposite, at the end, you need to get rid of the pump so that you do not lose too much useful pump in the cladding mode stripper. Let's move to model spectra analysis, which can provide us with better physical insight into the pump absorption. We will see it from another perspective, from the perspective of individual modes. Modal field approach is based on the work of Veit and Fleck here. And it is as follows. Firstly, let's have some reference field that background our double-clad fiber. In this case, it is a hexagon. You can see the narrow circumference of hexagon here, which should have a model content as rich as possible. Ideally, it should contain all modes that can exist in the structure, and the field should be stationary. Secondly, we have our analyzed field. It is described as sum of modes, which each of the modes is characterized by propagation constant beta and its modal amplitude am. Let's later calculate correlation function of these two fields and calculate Fourier transform of this autocorrelation function. So this Fourier transform has a character of peaks in the individual propagation constant of our analyzed field, and this is what we can use in our model spectra analysis. So let's start with spectra analysis of passive hexagonal fiber, which is excited by fundamental mode of the bent fiber. As it is, the fiber is bent quite tightly. The radius of bending is 3 cm. The fundamental mode is shifted from the center to the side. As it is a fundamental mode and propagates without changes or coupling to other modes, it propagates without changes. So only the fundamental mode is excited along the whole propagation distance. So nothing happens along the fiber. When we twist the fiber, we can see that the model spectrum of the originally fundamental mode gradually spreads and some higher order modes are excited in the structure. In the bottom part of this figure, you can see some sinusoidal modulation. This is because the fundamental mode has different form depending on the orientation of the hexagonal fiber with respect to the spool. We can find the mode that is associated with the edge of the structure, and also the mode that is associated with the corner of the hexagon. As the fiber is twisted, these two modes are transforming from one to the other and vice versa, and during this transformation, which is not perfect, also some other high-order modes are excited. This of course happens not only with the fundamental modes, which is shown here, but also for the higher order modes that exist in the structure. So this is the mechanism which causes spreading of excited modes in bent and twisted hexagonal fiber. We can compare the situation in hexagonal fiber with the situation of circular fiber. In coiled fiber, there is no change both in hexagon and in circular fiber. But in the case of coiled and twisted simultaneously fiber, there is no modal broadening in the case of circular fiber cross-section, while in hexagon it is the opposite. There is a large or huge broadening of modal content along the fiber. It is because circular fiber is rotational symmetric, and as it is twisted, we have no geometry change, and so there is no modal transformation. Let's move now to a more practical case of doped fiber. It has a 12 micrometer core, doped with about 2000 molar ppm of ytterbium ions. The flat to flat dimension is 130 micrometers, and this fiber is excited by a speckle pattern that mimics the situation in pump delivery fiber, like the typical laser diode pigtail with 105 micrometer core. The pump wavelength is 975 nanometers. If we compare this case with the case of coiled fiber, where the refractive index is inclined, now you see that the refractive index is inclined, so the spectrum of modes is broadened. So this space is now filled with newly excited modes. This is because the inclination of the refractive index extends the difference between the maximum and minimum refractive index of the waveguide structure. So we have wider spectrum of modes that are allowed to propagate in the structure. However, you see again that the modes keep being separated. There is no mode mixing. Some of the modes are absorbed and some other modes are not absorbed, or they are absorbed only slightly. And finally, in the case of coiled and twisted fiber, so the fiber is simultaneously coiled and twisted, you can see a huge effect of mode mixing. As explained before for the example of only fundamental mode propagation in passive fiber. So this mode mixing brings about energy transfer from mode to mode, and effectively all the modes are absorbed in the active core during the propagation. Here you can see another set of figures for comparison of layout geometries. First column contains model spectra along the fibers, as we discussed on previous slides. The second column contains longitudinal cut of the fiber, and the cut is made through the core and perpendicular to the spool, which is always on the top of the figures. In straight fiber, the pump spreads across the whole cross-section of the fiber. In the coiled fiber, the pump is squeezed to the outer part with respect to the spool. And in the case of simultaneously coiled and twisted fiber, the pump field is squeezed, and then it also traverses the doped core thanks to the twisting of the fiber along the spool. The last column is the overlap, contains the overlap along the fiber, overlap with the doped core. For the straight fiber, the overlap with the doped core quickly decays. The decremental rate for the coiled fiber is somewhat lower, and the lowest decrease of the overlap, the overlap is almost constant in the case of coiled and twisted fiber. As a summary of this part about pump absorption in double-clad fibers, I would like to point out two things to remember. First, pump absorption is enhanced by broken circular symmetry of inner cladding cross-section and by unconventional coiling methods. This is well known. But remember, non-circular fiber shapes do not help to mode mixing in strictly straight fibers and strictly bend-only fibers. This is one thing. And do not forget on pump squeezing and the decentering effect, as we have seen in the movie, of pump propagation in simultaneously coiled and twisted hexagonal fiber that is coiled on the spool. And the second thing to remember is approximation of cladding pump absorption. This is often mentioned in literature, and it is declared that the cladding pump absorption is constant along the fiber, and it is proportional to the ratio of the core area and cladding area. Sometimes it is declared that it is given by core absorption cross-section times this ratio of area. It is very helpful for numerical modeling and quick design of fiber lasers, but use it wisely. It is only an approximation. In fact, the truth is the opposite. The overlap factor gamma is never constant along the fiber, as we have seen in hexagon, so it deviates quite substantially from a constant behavior along the fiber. So for some geometry, it can get close for the ideal case. In this case, it was the geometry of the layout that is coiled and simultaneously twisted fiber on a cylindrical spool. Second half of the lecture, we start with limitations of double-clad fiber lasers. Double-clad fiber limits is closely connected to power scaling. Power scaling was the topic of previous lectures, so I will touch it only shortly. I like this graph of rise of power of ytterbium-doped fiber lasers that I borrowed from an outstanding review paper of Michalis Zervas and Christoph Kodemar. The red curve shows the rise of power of single-mode down-pumped fiber lasers that goes up to about 3 kilowatt. With advanced design of double-clad fibers, 10 kilowatts was demonstrated. Higher power can be extracted from single-mode tandem-pumped fiber lasers. They used their more brightness sources, typically one or multiple fiber lasers, pump another fiber laser. So, for example, here thulium-doped fiber laser is used for pumping holmium-doped fiber. Multiple fiber lasers can be combined specially, and we can go up to with even higher power. For the record, the current record is 100 kilowatts. So at the moment, fiber lasers are the highest power laser that is commercially available now. But of course, it is at the expense of beam quality, this especially beam combination. Yellow circles stands for coherent beam combination, so multiple fiber lasers are combined coherently, so the output beam quality is preserved. Here we see a tandem pumped fiber laser presented by IPG Photonics. They used master oscillator power amplifier scheme, so the first two stages are pumped with laser diodes, and they brings the signal power to about kilowatt power levels, and the final stage is pumped by several ytterbium-doped fiber lasers at 1018 nanometers combined together, and they brings the power to 6 kilowatts. They also demonstrated the output power up to 20 kilowatts with similar scheme. Here you see the traditional pump regions by laser diodes at 950 nanometers and 975 nanometers. The quantum defect with respect to the laser wavelengths at around 1070 nanometer is not very big, it's quite low, but at high powers even such a low quantum defect makes a problem with the heating. So they pump it at even closer wavelengths at 1080 nanometers, and so in such a way they decrease the heat load even more. Among the main power scaling limits belong the nonlinear effects. For continuous wave lasers, it is the stimulated Brillouin scattering and stimulated Raman scattering. For pulsed regime of operation, among others, it is self-focusing and self-phase modulation. Nominally, the threshold of Brillouin scattering is about 500 times lower than that of Raman scattering, but stimulated Brillouin scattering is a narrow band effect, so often the Raman scattering is even more limiting factor than the Brillouin scattering. How to mitigate these nonlinear effects we can see from these formulas for thresholds. So in the denominator you can see lengths. So if we have better pump absorption, we can use shorter fibers and we can mitigate the nonlinear effects by making the fiber amplifier or fiber laser shorter. And here in the denominator we see effective model area. So if we have larger model area, we can mitigate the nonlinear effects very efficiently. So the nonlinearity issue remedy is mainly the large mode area fibers. Here you see the profile of a standard single mode fiber at 1 micron, for example the Corning High 1060 with a numerical aperture 0.14 and core diameter slightly more than 5 microns. We have effective area of 30 microns. We can enlarge the mode area by decreasing the refractive index difference. So we have a fiber with 12 microns diameter, still single mode, and the effective area is more than 5 times larger than the standard Corning High 1060 fiber. It has little sense to decrease the refractive index difference even lower, because then the numerical aperture is so low that the fiber is very bend sensitive. The losses become higher with bending. So unless the fiber is very straight like rod type fibers, we will have very lossy fibers. But we can increase the core diameter even higher at the expense of few mode operation of the core, but we can suppress gain or propagation of the higher order modes. And here you can see measured refractive index profile of the standard fiber and of the one of large mode area fiber. Higher order mode filtering by coiling is another example that coil geometry is so important. The invention of large mode area fibers, and especially the methods how to maintain single mode operation of LMA fibers, is one of the major breakthroughs in power scaling of fiber lasers. So with the LMA fibers with about 50 to 100 micrometer core diameter, one can easily get about 10 dB decibel suppression of higher order mode propagation by coiling in about 4 centimeter diameter coil. Other method of single mode regime of few mode core was developed by, for example, tapering of the few mode fiber, gain preference, multi-trench fiber design, chirally coupled core, twisted fiber with broken circular symmetry of the core, or resonant filtering by leakage channel fiber and others. But most widely used and experimental simple is still the higher order modes filtering by coiling. By tight coiling, we got single mode operation of few mode fibers at only little expense of additional loss, but we have to account for squeezing of the effective area due to coiling. So we can see here examples of fundamental mode profile for 30 micron diameter fiber and 50 micron diameter fiber, and we can see that for the 50 micron diameter the mode area squeezing is much higher than here. The field is squeezed less than in this case. Do you remember mode area squeezing in inner cladding of double-clad fiber? So despite much larger core size, the effect is also important and the pump field is squeezed to the side of the fiber. Here you see an illustrative figure of the equivalent index model. It provides an intuitive picture of bend-induced distortion and model area reduction. So the bend leads to an index gradient across the core, which tends to push light towards the outside of the fiber band. Fiber index profile is the black line. The top blue line is the fundamental mode effective index, and the red line is the effective indices for the first higher order mode that is effectively leaking. So here you can see the effective model area with respect to the bend radius. The red curve is for the larger core, 15 micron core, and the blue line is for the 13 micron core. So the effective area is squeezing with tighter bend radius, but the squeezing effect is more pronounced for the 50 micron core diameter. The larger the diameter, the more it is squeezed with bending. So here we see plot of effective model area as a function of core diameter for varying bend radii. Core and the model area for straight fiber increase considerably with core diameter. However, for bending, the limitations become rather strict for fibers thicker than about 30 or 40 micrometers. When bending is such a big limitation, what about to make something between fiber and bulk optics? And here comes the rod-type large mode area fibers. Rod-type fibers made records in mode area scaling in active fibers. Note the blue-violet light coming out from the ytterbium fiber laser. So it is another example of rod-type fibers here. So the air-clad forms pump core or inner cladding of about 200 micron diameter, and the air-clad is connected to the outer material by 400 nanometer thick bridges, and this air-clad provides 0.6 numerical aperture for the pump. Look at the sparsely distributed air holes in the inner cladding. They provide slightly lower refractive index than that of the core. So the hexagonal core has 80 micron distance between the corners, and it gives the effective area as high as 4,000 square microns. Heating. Heating is a problem. Everyone who works with medium or high power fiber lasers has to deal with this limitation. But basic understanding of thermal diffusion is not difficult. You don't need sophisticated software to estimate it. So let's consider a basic double-clad fiber geometry with 2 claddings and 3 surfaces, and surrounding temperature of the background or boundary is Tb. Then you got the temperature in the core that is proportional to the square of the radius. You have quadratic dependence, and in cladding the dependence is logarithmic. The weak point is the silica and polymer boundary. The polymer gets brown at about 80 degrees Celsius. This is a signature of potential failure or even flame that is coming. So for what heat load you can get browning? So you can see here that with increasing diameter of the inner cladding, you can allow higher heat load in your fiber. Now I will show you temperature distribution for various fiber types calculated by finite element method modeling. It was modeled by Martin Grabner, who will have a presentation about tandem pumped octagonal double-clad fiber on Wednesday, so you are welcome to visit it. This graph just manifests that analytical model gives the same results as the finite element modeling. And the green line is for thicker inner cladding. This is temperature profile of octagonal fiber with 10 micron core and a 130 micron flat-to-flat distance. 100 watt per meter heat load is too much. You see that we got about 90 degrees Celsius at the polymer boundary and more than 125 degrees Celsius in the core. With 250 micron inner cladding, we should be below 80 degrees Celsius at the polymer boundary, and we got also colder core for 100 watt per meter heat load. This is fiber heating in air-clad fiber. We get a temperature step of several tens of degrees of Celsius in the air holes because the heat has to be pushed through narrow silica bridges. It should be pointed out that the heat load is of course not the same at every point along the fiber. But even in the record experiment with more than 1 kilowatt average power thulium fiber, it was estimated to be below 200 watt per meter at every point along the fiber, and on average it was even less than 100 watt per meter in 50 micron core and 250 micron inner cladding thulium photonic crystal fiber. Heat load and thermal issues stay behind other highly important limitations of double-clad fibers, especially large mode area fibers. It is the thermal lensing and transverse mode instability. Here you can see refractive index profile of the coiled fiber and corresponding transversal distribution of the fundamental mode field. Heat causes increase of refractive index through thermo-optic effect, and correspondingly the fundamental modes get shrinked towards the axis of the fiber, and this is the thermal lensing effect. Above certain threshold, transverse mode become unstable. The modes of such structure starts to oscillate with frequencies in about kilohertz range. For even higher power, the modes fluctuates chaotically. The TMI effect was discovered about 10 years ago in Fraunhofer Institute in Jena. Transverse mode instability is caused by creating a fiber grating with grating pitch orders of magnitude longer than the laser wavelengths responsible for grating buildup of the order of millimeters or centimeters. Such long-period fiber grating enables coupling between different transversal modes of the fiber core propagating in the same direction. The grating is not static. There is a phase shift between the modal interference pattern and the dynamic grating, and the sign of this phase shift determines whether the energy flows from the fundamental mode to higher order mode or vice versa. Here you can see the threshold of TMI and thermal lensing with increasing fiber core diameter. And you can see that the thermal lensing threshold is above the TMI, so the TMI is more limiting effect. And TMI threshold decreases for larger cores, so very large mode area fibers are more severely affected by TMI. However, TMI threshold is not given only by fiber design, but it is determined by the whole laser device configuration. So not only transverse modes of the fiber can be unstable like this, we may observe also instability of longitudinal modes. And in longitudinal direction we have thousands of modes of the fiber. We know various regimes of longitudinal mode oscillations. One of them is laser wavelength cell sweeping that you can see here in a real-time movie. It is a spectrum of ytterbium fiber laser of similar setup like this. And the wavelengths of the laser is sweeping continuously and slowly from about 1074 nanometers to 1084 nanometers, and then it jumps back. Above laser threshold, longitudinal modes may become unstable. The actual lasing mode starts to change with frequencies in about kilohertz range. For even higher power, the modes fluctuates chaotically. The cell sweeping effect was discovered in fiber lasers about 10 years ago by 3 laboratories independently. The longitudinal mode instability is caused by creating a fiber grating with grating pitch of the orders of the laser wavelengths, responsible for the grating buildup. And such fiber bragg grating enables coupling between different longitudinal modes of the fiber core propagating in the opposite direction. the grating is not static, there is a phase shift between the modal interference pattern and the dynamic grating, and the sign of this phase shift determines whether the energy flows from the mode with shorter wavelengths towards longer wavelengths, like in this video, or vice versa. Self-sweeping operation is not given only by fiber design, but it is determined by the whole laser device configuration. Here you can see output of such self-swept laser recorded by an oscilloscope. Just above threshold, we have more or less a regular train of microsecond pulses at kilohertz repetition rate frequencies, and with higher output power, it is turned to chaotic train of nanosecond pulses with kilowatt peak power. So be careful when you build a continuous wave fiber laser. You may get unexpectedly self-Q switch regime with giant pulses that may easily destroy your laser, inline components, pump diodes, and also your measurement equipment. Ytterbium fiber lasers are particularly notorious in this regard. Here we have basic energy level diagrams of most frequent rare earths used in double-clad fibers. Neodymium typically emits at around 1060 nanometers, ytterbium emits at around 1070 or 1030 nanometers, holmium at 2.1 micron, erbium at 1550 nanometers, and thulium at around 2 microns. Double-clad fibers doped with thulium are often pumped at photons with more than twice as high energy than the final laser radiation. So it seems to be very ineffective at first glance. However, with sufficient thulium concentration, one excited ions to this 3F4 level may share its energy with a neighbor. So the quantum efficiency is effectively doubled. This is the so-called 2-for-1 process. Every dopant often faces specific challenges. So, for example, when you solve problem for erbium fiber device, it cannot be automatically transferred to holmium fiber device, and you have to investigate the problem newly for holmium. We haven't time to discuss many challenges, so at least one: the photodarkening. Photodarkening is a permanent light-induced increase of absorption of the fiber, like you see here for ytterbium. This is for pristine fiber, and this is the excess loss of the used fiber. It is a multiphoton process that involves the rare earth ion. It was observed in ytterbium, thulium, and some other ions. It is caused by formation of color centers, and the rare earth ion gets energy directly by photon absorption or by migration process from a neighboring excited rare earth. High inversion of population increases photodarkening rate. So photodarkening is slow in continuous wave double-clad fiber lasers with a low average inversion, but it is fast in amplifiers or broadband sources like amplified spontaneous emission sources and in core pumped fiber laser devices. So it can be mitigated by material composition and also by device configuration when you design the laser device in such a way that it operates at lower inversion. So pump combiners. These components are so closely connected to the geometry of double-clad fibers that sometimes the double-clad fibers are even designed to match especially the pump combiners. We will spend a few slides in these components. In principle, we can divide combiners after the direction from where pump enter the fiber, either from the end, as an end pumping, and from the side pumping scheme. Eli Snitzer pumped his fiber with asymmetric core by bulk optics. One can add a dichroic mirror so that the signal mode can be added. However, this bulk setup usually requires adjustment and realignment from time to time. So here we miss the beauty of all-fiber alignment-free configuration. Highly practical is a star combiner that combines a ring of pump fibers around the signal fiber, and it was developed in Bell Laboratories. Double-clad fiber can be end-pumped by direct splicing of pump and signal fiber, so there is no need for a combiner at all. But it's better to have a double-clad fiber with cross-section similar to the input fibers, like it is the stadium here. The second group is side pumping. The beauty of this combiner invented by Gapontsev and Samartsev is that the signal fiber goes through the combiner and the modal field of the signal is almost unchanged. We can couple pump from the side by some refractive or diffractive element like the V-groove here. And commercial successful side pumping is also the so-called GT-wave fiber structure with multiple individual fibers bundled together. Star combiner is made by tapering bundle of pump fibers with signal fiber in the middle. The tapered fiber bundle is then cut in the taper waist, and spliced into a double-clad fiber so that it forms the combiner common port. It is great that all ports can be spliced to other fibers. Problem is that the signal fiber in the middle, as it is tapered, the mode field diameter of the guided mode is changed. The problem was solved ingeniously by splicing a special fiber in this section. So the splice is even before the start of tapering section. This graph shows how mode field evolves with tapering. So at the beginning, the fiber has core with 12 microns. As it is tapered, the mode field diameter shrinks to about 7 microns, and then relatively fast it expands, and for 4 microns it is back to 10 microns. So with this mode field adapter, one can get transmission close to 1. It can be further improved, for example, by proper positioning of the splice within the taper. Or another method is based on fiber core fattening by dopant diffusion with heating or by vanishing core technology. Now you see the advantage of the combiner with signal feeds through. Here you do not need mode field adapter at all. Moreover, this scheme works in wide spectral range, while mode field adapters have insertion loss that vary with wavelengths more significantly than this. How it works and how it is fabricated. So multi-mode fiber is first spliced to a coreless silica fiber that is pre-tapered, and the taper is coiled around the double-clad fiber. Under heating and under small tension, the pre-tapered part is buried into the double-clad fiber. And how it works? When the pump light propagates through the tapered portion here, more and more modes become leaky modes of the taper, and they escape from the taper to the medium with high refractive index. It means that they do not escape to the air, but they escape to the double-clad fiber where we want. Coupling efficiency greater than 90% can be achieved routinely. The same rig for making fused biconical tapers can be used, for example with the oxygen and hydrogen flame. Note that such component was envisaged already in late 80s, as it was presented in Advanced Solid-State Conference early 1990 by Valentin Gapontsev, where he presented more than 1 watt from fiber laser and predicted high power operation of the orders of tens of watts. This is another testimony that the term high power has relative perception, especially in the view of kilowatt power operation available now. Excellent description of this method, including ray tracing modeling, was presented by Thomas Tag in this paper. From this paper you can see the top view and the cross-section view of the fiber combiner with 4 pump ports. Several techniques have been developed for launching pump light using mirrors or diffractive elements. V-groove can be milled from the side of the double-clad fibers, and then the pump laser diode can be focused on one facet, so that we get unidirectional propagation of the pump, or to both facets, so we got bidirectional pumping. This approach is not scalable to very high pump powers, only of the order of tens of watts as far as I know. Coupling by grating or prism was tested, And here you see approach of embedded mirror side pumping. These elements can be aligned side by side so that it matches the bar of laser diodes. Pump and signal fibers can be spliced directly to the double-clad fibers. Here you can see the pump fiber with 105 micrometer core and standard signal fiber. It can be spliced with low loss to double-clad fiber that resemble the shape of stadium. Standard fusion splicer can be used. We need only special grooves with flat bottom. Completely different in principle is the GT-Wave double-clad fiber bundle structure. It is a multi-fiber arrangement. It is not a single fiber, and the pump coupling is distributed along much longer lengths of the active fiber than in all the other cases. The GT-Wave structure has at least two fibers, one for pump and the other for the laser signal. Look at the cut where the pump fiber and the signal fiber is spliced to the loosened ends of the GT-Wave. The pump and signal fiber are twisted either after drawing or preferably when the fiber structure is drawn from preforms at the drawing tower. Twist is important to keep the fibers together, but also the twist is important for efficient pump coupling, as we have seen before in the part of pump absorption. It is nicely supported also by numerical modeling. While only negligible absorption we can observe here in the green line for straight fibers, we got a very efficient pump absorption when the fiber bundle is twisted. See the blue line here. Short amplifying modules with a length of about 10 cm were fabricated using rare earth doped phosphate glass fibers with high concentrations of active ions. It has great advantage for short pulse amplification. It works in medium power levels of up to about 10 to 20 watts. We are coming to the double-clad fiber technology. Most of the double-clad fibers are fabricated in two steps. Firstly, a preform is made. It is a glass rod with about centimeter in diameter, and typical length can be several tens of centimeters. Preform has the same cross-section as the final fiber, but about 100 times larger. Secondly, the preform is heated by graphite furnace to about 2000 degrees Celsius. The end of the preform is slowly dropping, and as it comes down, it pulls the fiber. Preforms can be fabricated by different methods. We use mainly MCVD method in combination with solution doping method. MCVD allows to prepare high purity material of the preform. Starting materials are high purity liquids, usually halides. They are kept in these flasks, the bubblers, and their vapors are taken by oxygen flow into the substrate tube. The vapors react in hot zone of the oxygen-hydrogen burner, and the soot sits on the inner walls. Because the tube rotates, the soot forms a porous layer. Rare earth compounds are too heavy to be transported in the same way. One way to put them into the soot layer is the solution doping method. So it means that the tube is taken out of the lathe and solution with rare earth salts impregnates the porous layer. Later, back in the lathe, it is dried and sintered. And finally, the tube is heated even more so that the tube becomes viscous and it collapses into a rod thanks to surface tension. Other methods are plasma chemical vapor deposition, outside vapor deposition, chelate delivery, hybrid gas phase solution doping, direct nanoparticle deposition, sol gel methods, or sintered powder methods like Repusil and others. I will mention in more detail only one from the other methods that use ceramic nanoparticles, typically alumina nanoparticles, in the solution instead of alumina chlorides. Here you can see original figure from the IEEE Laos conference in 2007. Two ways were proposed about the nanoparticle dispersion. Firstly, alumina nanoparticles plus rare earth chlorides, and secondly, newly synthesized alumina nanoparticles that already contain rare earth ions. Finally, it was desired to have the rare earth ions encapsulated in nanoparticles in the core, so both ways should result in the same. Maybe, or most likely, the nanoparticles will not survive high temperature during the collapse and drawing. But anyway, it helps to incorporate high concentration of alumina, about 5 times or even more than standard solution doping method, and also more rare earths into the fiber. Nanoparticle doping method and also other advanced method allow more than 10 molar percent of alumina and more than 1 molar percent of thulium, so that we got higher delta N than it is desired. Look at this refractive index profile. We got refractive index difference 0.021, which corresponds to numerical aperture of 0.25, but for large mode area fibers we need 0.06 numerical aperture. So what is the solution? Should we dope it less? Well, it is possible for some cases like ytterbium doped fibers, but it is not possible for thulium. So this is the refractive index for large mode area fibers. It is less than 2000. And here we have more than 10 times higher refractive index profile. How we can get large mode area fiber with this large refractive index difference? Thulium double-clad fibers are efficient thanks to so-called 2-for-1 process, where one pump photon generates 2 signal photons. However, it works only for high thulium concentration. The solution of this problem is pedestal refractive index profile, so that the fundamental mode of the core, this is the core, sees the refractive index of the pedestal and not too much the refractive index of the silica inner cladding. If we have larger pedestal, like here on the right figure, it is better for laser performance, better splicing and higher order modes discrimination. But large pedestal is more demanding to fabricate. This is schematic of the drawing tower. At the top we put the preform to the graphite furnace, and from the heated zone the fiber is drawn. Below the furnace we have a measurement for the diameter. This is connected via feedback with the capstan, so that the fiber has constant diameter. This is coating die, so that we can put a polymer onto the fiber. This is curing furnace for curing the polymer. We are going to see a short video about what we have heard so far. So this is the bubbler with starting materials. You see deposition of layers on inner wall of silica tube. Another view of deposition of layers. Collapse of deposited tube. Now we are going to a drawing tower. The preform is heated up to 2000 degrees Celsius. And this is the glass drop that pulls the fiber. Look at this part. This is not a pure silica. This is a part of standard glass that is connected to the pure silica. So it works like a weight that helps to pull the fiber down. Here it is UV curing of polymer coating. And finally this fiber is winded on a spool. We have seen a short overview of optical fiber technology that is similar to standard fibers also, but now something special to double-clad fibers, and it is shaping of optical fiber preforms by grinding or milling. So first, this is standard method grinding by diamond plate. The outside interface of the pump core can be constructed from a rod-shaped preform, this is the initial preform, by local melt displacement using an open flame. This is pictured from the patent, and here is an example of the cross-section of the drawn fiber. Another thermal shaping profits from a high absorption of the silica glass at wavelengths around 10 microns of CO2 lasers. The CO2 laser beam comes from here, and is focused on a preform that moves horizontally. The silica fume is sucked by a collector pipe, and when one groove is finished, then the preform rotates and another groove is polished. This setup was developed and it is operated by Ali Yasim and Pavel Honzatko, and a special acknowledgement belongs to their perfect works. We were inspired also by work of Peter Shardlow in University of Southampton. This technique allows shaping preforms with concave and convex structures. It offers short time of process, depends on laser power, and it is a fully automated process. Here you can see a couple of cross-sections of drawn fibers. So hexagonal with shallow grooves, hexagonal with deep grooves, octagonal or decagonal cross-section. Main types of second claddings are low-index acrylate coatings. It offers high numerical aperture of 0.46, but it gets brown at less than 100 degrees Celsius. And unfortunately, it has high attenuation above 1.6 microns, so it cannot be used for tandem pump thulium or holmium fiber lasers. The other type is fluorine-doped silica cladding. It offers lower numerical aperture, so lower pump can be coupled into these fibers, such fibers, but it withstands high temperature. Very high numerical aperture of the inner cladding can be achieved in the air-clad double-clad fibers. The numerical aperture is determined by propagation constant of the first excited mode in the capillary bridge here. This example, published in 2004, has inner cladding diameter 114 microns and the width of the bridge is 220 nanometers. It corresponds to almost 0.9 numerical aperture at typical ytterbium pump wavelengths around 1 micrometer. We come to the part of characterization. This is a very important part and it would deserve a special lecture, but we have time to mention just a few tips specific to double-clad fibers. In the preform, we measure refractive index profile by measurement of deflection function. So we measure deflection of beam, for example, deflection of a helium neon beam that is deflected by the preform. And we can calculate from the deflection function also the tomographic reconstruction of the refractive index profile. Here you can see preform for almost stadium-like preform and fiber. But of course, we are mainly interested in the refractive index profile of the core. The outer shape we can determine other ways, not by refractive index measurement. And we also measure concentration profiles by electron microprobe analysis. Here you can see measurement of absorption by cutback method, so of the fiber of thulium doped fiber. So we know the spectral profile, spectral shape of attenuation of a fiber of length L. We know the concentration in the core, and we can calculate overlap of the signal propagating in the core with the doped area. And so the only unknown is the absorption cross-section. So this is the core absorption cross-section. Please note that I will not speak about cladding absorption because this we have discussed in detail in the first part of the lecture. In double-clad fibers, we can come to some problems that stems from high concentration. So we can't use long lengths because we will then extend the available dynamic range of the measurement. There is some problem with high power broadband sources or even with halogen lamps with re-emission of radiation. So this is reviewed in a very good paper by the group of Johan Nilsson. Anyway, the traditional cutback method in its pure form is often not suitable, so one has to modify it somehow. The cutback method, for example, we used a very short piece of double-clad fiber that is pigtailed from both sides by single mode fibers, so we can then measure with high resolution these absorption curves. When we come to emission, the emission spectral shape has also some things that we need to account for. For example, when we measure the emission spectral shape, we need to use very short fibers. The length of the fiber should be about such length that we have 0.2 dB small signal loss. So it is really very small fiber, sometimes a millimeter or so. So this is the spectral shape of emission from thulium, and this I showed this figure in order to point out the importance of correction. So if you measure it directly from your setup, you got this black line, but if you correct it for wideband coupler and sensitivity of the detector, only then you see the final spectrum. So although the wideband coupler and detector is almost flat, you need to take it into account, and you see that the peak is shifted by about hundreds of nanometers to the short wavelengths. The absolute value can be measured by measuring gain in fully inverted fiber, like it was described, for example, by Giles and co-workers from Bell Labs in early 90s for erbium fibers. But again, think wisely, if it is really fully inverted fiber. Sometimes the very highly doped fibers have important cross relaxations, so it's not fully inverted. So we do not use exactly the same procedure as it was used in this paper. Or we can estimate the absolute value by Jutterfeld theory and Furchtbauer-Landenburg formula. But it is only an estimation with several tens of % uncertainty. We can estimate the emission cross-section. For example, here you can see it for holmium fiber. We can estimate it from Mecklenburg theory from the measured absorption cross-section. So if the two peaks are close together, one can get quite reliable estimation of emission cross-section from the absorption by this formula. This was first demonstrated for erbium fiber, and it is valid also for holmium fiber, but you can't use it, for example, for thulium. Another important parameter is the fluorescence lifetime. For example, in thulium, if you measure fluorescence lifetime in the metastable level for 2 micron lasers, the 3F4 level, so usually you have so much doped thulium fibers that you can use the so-called side detection. So here is the excitation diode. You excite it by square pulses to this level, and you measure the fluorescence decay from the side in thulium fibers. So here you can see this excitation pulses, and here you have the fluorescence decay. But because of some cross-relaxation effects, the beginning of the curves are not pure single exponential. So when you would like to measure the 3F4 level, you should fit the tail of the fluorescence decay. We still have some time to show some selected emerging technologies. I apologize that so many interesting topics will be missing. Here we see a cross-section of double-clad fiber for almost 10 kW single-mode diode pumped fiber laser. It has 8 pump parts that surrounds the central part with the core. It is another example where pump absorption is so important, and it is tailored along the fiber. So at the beginning, the pump propagates still around the central core, so we have a lower pump absorption where the pump is high, and the pump absorption is increasing along the fiber. Another emerging technology is nanostructured double-clad fibers. Here you can see the technology steps. It looks like a standard second-order method, but it has some important differences. For example, the density of nanostructuring is so high that from the point of view of wavelengths, it looks like homogeneous material. There are still some unresolved issues in this technology, dealing with materials, geometry, spectroscopy, and applications. Double-clad fibers that we have discussed so far were mostly based by silica fibers, but silica is not transparent beyond 2 microns. So for fiber lasers between 2 and 4 microns, another materials, host material, must be used. In this case, it works well in Z-blend fibers, in fluoride fibers. So for example, this is schematic of a 3.5 micrometer laser that is pumped by dual wavelengths. Promising technology is crystalline double-clad fibers. It can resolve potentially some silica fiber drawbacks. For example, YAG crystalline fibers has 100 times lower gain for stimulated Brillouin scattering. It has 10 times higher thermal conductivity and it allows high rare earth doping. So we have discussed quite a lot thermal issues and heat removal in fibers. So a very important and big research field is development of advanced coatings. Here you can see cross-section of octagonal double-clad fiber that is coated with protective aluminum coating. And with such an advanced coating, you can reach about 40 degrees Celsius lower temperature in the core in metal-coated fiber with respect to the fiber that is coated with standard polymer. Other important topics are multi-mode Raman fiber lasers and tapered fiber amplifier, which also solve the issue of tailored pump absorption and also mode area scaling along the fiber. And this is the final slide of my presentation, and with this picture I would like to acknowledge my colleagues. I'm so grateful to Pavel Honzátko, Ivan Kašík, Ondra Podrazský, Ali Jásim, Michal Kamrádek, Honza Aubrecht, Filip Todorov, Pavel Koška, Vlastimil Matějec, and all other current and former colleagues in the team of fiber lasers and nonlinear optics of UFE. And of course, I thank you for your attention.